Good morning to all participants from myself and Katarina. My name is Phiweek2021, and I work for ESA in the Data Application Division.
Yes, good morning indeed. Welcome to this race side event. My name is Katarina Bams. I work for the Commission in the Earth Observation Unit in the DG called Defense Industry and Space. So we're doing the welcome word today, Yves-Louis and myself. So Yves-Louis, can you enlighten us a bit about the RACE initiative? What does RACE stand for and when was it launched?
Okay, RACE stands for Rapid Action on COVID-19 and Earth Observation. It's an initiative which was launched in spring 2020 by the European Space Agency and the European Commission.
Okay, that's a good start. Tell us a bit more. Does it use Earth observation data? I already know the answer, but
Yes,
is it publicly available? Can you tell us a bit more about that?
Yes, of course, its objective is to use Earth observation data to monitor and understand the impact of the pandemic on society, but also on the economy and environment.
Okay.
Means all the outcomes of the work and investigation are presented on the publicly available RACE dashboard at race.esa.int, which is a kind of interactive platform where you can really play with the data and retrieve information derived from mainly the Copernicus Sentinel, but also third-party missions and other open data sources. Today, the project includes contribution from over 40 companies and institutions, and we have reached a number of 128 countries globally and is still growing.
Okay, thanks. But if I understand correctly, it also uses information products from our Copernicus services.
Of course, it also serves as a demonstrator of the complementarity between satellite Earth observation, modeling, the inclusion of several products from the Copernicus services, also open source data and various other kind of data such as mobility, mobile information, and of course we are using analytics technologies such as artificial intelligence.
Okay, so the RACE initiative started in 2020. What are the plans to continue once the pandemic is over? Will it transform into a new project?
Yes, the plan is actually to continue. We are building on this technology, so we have seen that we can deliver a lot of indicators for the economy and the evolution of the environment. And actually, the sister dashboard, which we have developed also jointly with NASA and JAXA, is going towards monitoring the environment and looking at some of the climate effects on society.
Excellent. Okay. Tell me about the link, or is there a collaboration with the science community?
Yes, from the outset, there is a strong connection to the science community. Actually, they are guiding us on how to use properly the data and state-of-the-art algorithm. So this is really one key feature, a strong science component and getting recommendation from these scientific groups. A second component is really the engagement of the public, which we have done through a series of what we call a competition or contest, we call them in the race environment. So these competitions participants are invited to use the open data and some computational resources provided via the Eurodata Cube. And they can process the data and deliver innovative solution. And actually, two of the most innovative solutions derived by the public will be presented today.
Okay, excellent. Talking about today, we don't have a lot of time, so let's quickly race through the agenda. I see these are very short presentations, so that's light. We always like that, I think, to be concise. The first agenda item I see, it's a presentation on the RACE dashboard project. So it will be a demonstration what RACE can do. Is that correct?
Yes, indeed. The next presentation then will deal with the Eurodata Cube, which I think I could stress how important it is because the data are ready to be analyzed and processed and organized in a cube fashion.
Okay, and the next agenda item, what will be presented under the showcasing newest indicators?
As I was mentioning, we have a growing contribution from industry, and we are going to show some of the newest indicators on oil, agriculture, environment regarding air and water quality.
Excellent. Then we will jump into the world of the Copernicus services, I see. There will be a presentation from our Copernicus Atmosphere Monitoring Service and from the Marine Environment Monitoring Service.
Yes, so we will also follow by the race challenge and the European Data Cube workspace for the challenge. And there will be two presentations, one by ESA about the contest approach and the second by industry on the use of the EDC.
Okay. Last but not least, can you tell me then what will be dealt with in agenda item 9?
So 9 is about public contribution to the dashboard.
Okay.
And it's about truck and flying airplane and vessel detections.
All right. And then there will be a brief Q&A, I understand, if there are questions all over these presentations. And so I don't know if Louis, I think, thank you very much for the brief explanation. So I would say let's not keep the public and the speakers waiting any longer. Both Yves Louis and myself, we wish you a very fruitful session. Thank you very much.
Thank you.
Thank you. Then I will just jump in and share my screen. I hope that you can see it well.
Perfect.
Okay, so great. So my name is Anka Angela. I am leading the technical development of this dashboard. So I will just make a very short review, let's say, of what this project is about and just give a very, very short demo. Not to repeat what was already said by Yves Louis and Katarina. So this project is called Rapid Action on COVID-19 and Earth Observation. It's basically a project where we try to demonstrate what we can achieve with Earth observations in terms of looking at the impact of the pandemic. And what I would like to stress on this slide is actually the thing that I've highlighted here in yellow, so the link to the GitHub, because the main message that I would like to transmit in this short presentation is that this is a collaborative project. So this is an open source project. We invite contributions through the various activities that we launch with the competitions, with the challenges, but also directly from the dashboard itself. We have included a possibility, so we have a feedback button there that takes you directly to GitHub. And we would really like to see this project used and reused, let's say. So I will just jump to the next slide. Just to point out the main idea that was behind the project. So we were aiming to make use of the whole range of Earth observations that we have available, mostly from Copernicus services, from Copernicus Sentinels, also using Copernicus services data, and to transform this information into something that can be very easy to understand by the general public. So let's say we made a translation from the Earth observations and the satellite information into something that is, let's say, in the language of the citizen. So this dashboard that we developed includes a wide range of indicators from economy to environment and health as well. And it's all presented in a very interactive way, also linking to the Earth observations that stand behind those information. So we have a large number of companies that have contributed. They're shown here on this slide. I will just play a very short video just to showcase the interface. So there is this central map panel where you can see all these pins where we have locations with data and the countries that we cover. It's basically the whole of Europe, and the number of indicators that are either presented on a per spot basis or global indicators, basically maps data. So all the list of indicators is accessible from the interface, and you can just go to each location and look what data is available there. Inspect the graphs, interact with the graphs, but also look at the Earth observation data that is behind. So for some of the indicators, we use machine learning, such as this one, where we have object detection. But you will see a lot of this in the coming presentation, so I will not insist too much on this. What I would like to stress is that the project is based on a lot of open data. So the most used data in the project comes from the Copernicus Sentinels. We have all the Sentinels, or almost all of them, that are flying, providing data for this dashboard. We have also contributions from the Copernicus services, as well as statistics data, health data, population density, mobile analytics, AIS, and so forth. Just to remind that we have two community contributions that will be shown today. So one is on the truck detection and one is on moving airplanes. They both exploit the same very cool artifact in the Sentinel-2 imagery, and you will hear a lot about it. This is just to point out that, again, that this is a collaborative project. And this enables me to introduce the last point that I would like to make, and the last demo that I would like to show, which is on this feature that we recently released. It's called the custom dashboard, and I will just play this video and speak on it. So here we have introduced the possibility for participants to, for users to add indicators to a custom view. So I included this little button there that was called Add to Custom Dashboard. And once you add these indicators to a view, you can just interact with the elements, move them around, zoom into the places where you want to inspect, and also go back to the dashboard and add some more as you want to customize the dashboard. So in this example, I was focusing on Italy. So I'm just browsing through the dashboard, selecting Italy as a country, looking at which indicators are available for this place, and then just adding, keeping adding indicators to this custom view. There are a lot of things that we can do, like customizing the titles of the elements that we want to add, and just including whatever information we want. There is also the possibility to add customized text and images to this custom view. And finally, when we are happy with the selection of data that we want to add, for example, now we're looking at what could be relevant if we combine air quality data with humidity. So I'm just browsing through the humidities. I'm seeing that I have some CDS data available on Italy, and I decided to add it to the dashboard also. And if I'm happy, I can just go back to my custom view and then customize a bit how I want the elements to look, fix the map position since I'm interested in Italy, and then maybe I just jump a bit to the end. So when I'm happy with all the selection that I've done, I can just save this dashboard. Give it a title as I wish, indicate there some of the interests that I have, give my name and my email address, what I will receive. Finally, the links to be able to go back to this custom view and share them maybe with my peers so that we can collaboratively edit on it. So I've copied the view link here. And now if I am a team member, I can just go back to this URL and have access to exactly the same view that my teammate made and inspect the same locations as before. So this is what I wanted to show. You will hear a lot more about this in the coming presentations. Thank you very much for listening to my talk, and we're here for your questions. Thank you.
Thank you, Anka. So I take over? Is that correct?
Yes, so next presentation is from Synergize. Rega.
Perfect.
Thanks.
Just to start the screen. Can you confirm that you see my screen?
can, yes.
Perfect. Thank you very much, Anka, Ivlui, and everyone else at the call. So I'm Gregor Minczynski. I'm coming from Synergize, and I'll quickly drive you through the EuroDataCube platform, which is providing the technical support to the whole race initiative, actually. So when we were starting the EuroDataCube project a few years ago, what our main objective was to basically make the EO data used to the capacity that it should be used, right? Because we believe that, or we noticed that it's significantly underutilized based on how valuable it is. And to do that, we knew that we first need to get the data available to anyone just to get familiar with it so that they can really explore and understand it. Then to create tools that allow them to build on the ideas that they have, to analyze, to create algorithms and so on. And then in order to be able to create applications so that they can then provide the information that they extract from the data to others who are maybe not as technically savvy in terms of the Earth observation. So in a nutshell, what the EuroDataCube is now is a set of applications, API, libraries, which provide more or less all the functionality needed for the processing of Earth observation data. I mean, there is not one tool that fits everyone, so we created several, and then simply the one chooses those that fit them best. The idea is that you go to the Jupyter notebook, you create a prototype there, but you're also able to scale up this on the large to the global scale if needed. You can do it on your laptop or in your favorite cloud environment or within the EuroDataCube itself. And it needs to be really said that EuroDataCube is not like a project, but rather it's a set of operational services, some of them pre-existing, some of them being built within this initiative. And they really are there readily used and useful and used by many, and therefore they should be used by you as well. Now, what EuroDataCube is really a set of tools. All of it is built on the cloud infrastructure, on the several clouds, integrating data coming from Copernicus, USGS, commercial sources everywhere. And then there are tools and services in place which provide access to the data, processing of the data, both raster and vector, right? It's not just a satellite. Then we have the hosted compute so that you can run some things directly in the EuroDataCube, Jupyter Lab, and all of this is available through a set of APIs, both the standard ones like OGC, but also the Python dedicated APIs, simply because the Python is most commonly used language in the Earth observation domain. So you can really do most of it. Now, it all starts and ends with the data, and we put a lot of effort to make as much data available as possible. At the moment, it's more than 50 petabytes, going for all all the open missions such as Sentinel, Landsat, MODIS, and alike, as well as integration with the commercial satellites, Airbus, Maxar, PlanetScope. But not just satellite data, also derived products like Copernicus services, and as well as the administrative data from the national organizations. And we put a proactive effort to expand this portfolio, to get more collections in, and to make sure that the data are always up to date, right? So it's not just support for this data, but for all of this, you can get access to full and global archives. And this is why it's like really 50 petabytes of data. Now, that being said, as much as we try, we cannot make sure that each and every collection will be there, which is why we have the capability to bring your own data, where you simply get your data in one of the supported formats, you put it on the object storage in one of the supported clouds, and then ingest it in the EuroDataCube, and then you can do everything with it as well as with the other missions. Then in terms of the services, you have Sentinel Hub for instant access to the Earth observation and other raster data, super easy to integrate in workflows and applications. You have Xcube library to provide extension into the wide Python portfolio of tools and open source libraries so that you can really get as much as possible out of it. You have GeoDB because, as mentioned, it's not just about raster data. Lots of the useful and essential data is in vector format, and we have GeoDB where you can store and process and access the vector data as well. Some are open collections, some are simply there to onboard by yourself. Statistical API provides super efficient way into long time series, so that if you need a couple of years of data over specific object, rather than working with pixel, you just get the statistics out of it. If you want to do something large scale, or if you want to create the features for the machine learning process, there's batch processing, where you simply define how you would like to have features configured, interpolated, harmonized, and what else. And then you say, look, I'd like to have this over this region, can be globe, and then have it running, and you in a couple of hours, you'll have everything readily available. There is hosted compute powered by UXF Workspace, where you get access to the actual virtual machines, both CPU and GPU powered, so that you can run some processes directly there. There is Jupyter Lab, full of quite useful examples in Jupyter notebooks from start to end using machine learning, as well as many of the things that will be presenting today, or will be presented today by others, are available there as examples as well. Now, we have launched this week the Bring Your Own Algorithm capability, and I'll invite everyone to check the recording once it's available if you haven't participated, which basically allows you to take your algorithm, which within the Eurodata Cube, you made it to work up to the extent that you can actually present it to others. And then you deploy it to the Eurodata Cube, and then you can simply make it available to everyone to use. You set your own constraints like commercial terms and pricing and whether it's free or not. And then it's there available for everyone to use, and you don't need to bother about that because it's taken over by the Eurodata Cube. It was designed in a way that you can then take these algorithms and chain them so that you really build on top of it rather than rebuild the stuff that was already done. Now, going back to the objectives. So when we started, we really believed that these things are essential. And I believe that we came quite far with it, right? So Eurodata Cube is powering, for example, EO browser, which provides like the most easy and accessible way to get familiar with Earth observation data to tens of thousands of people around the world every month who go and explore what's happening with our planet. Then we have the EDC browser, which is a more professional application similar to that, providing access to all the collections that are available in the Eurodata Cube in, again, a similar yet a bit more featureful environment. And there are already results. I mean, even just these applications provide some useful results, like these scientists who were looking for the penguin poo to identify new colonies in Antarctica, or this guy who used your browser to geolocate the photo of this hairy legs by a lost hiker and send the search and rescue team there, all powered by Earth observation data. Now, the tools that we made in place to allow exploring and analyzing and building were very nicely demonstrated in the COVID-19 custom script contest, which we run with ESA, and I think will be also described in this session. Where people came and were able to, from scratch, build their ideas into something that was really demonstrable. And several of these ideas actually came to the stage that they were fully operational, like track detection, which will as well be shown during this session, and are now deployed as a bring your own algorithm to the Eurodata Cube so that anyone can come and make use of it. Now, last but not least, when we have these algorithms working and the procedures, it's really essential to have applications so that you can extract the relevant information to the people who are, let's say, not bothered about the satellite data at all. They just want to get the information. And this is where the RACE dashboard, I think, is such a nice initiative demonstrating how it could be done, yet also providing the information directly. It's not the only application. There are hundreds of applications worldwide powered by the Eurodata Cube, and some of them will be described in this session, and I'm looking forward. Thank you very much.
Thank you so much, Grega. This was a really, really cool presentation. I welcome now Florian Thaler from OILX, who will talk to us about one of the economic indicators that were recently added to the dashboard.
Yeah, thank you, Anka. Can you just confirm that you can see my screen?
We can, yes.
Yeah, thank you very much for this opportunity. We are excited to present today an index, European Crude Oil Storage Indicator. It's an economic indicator to measure what happened to the energy supply chains during COVID, but interestingly, it also has its validity right now for those that follow the news, what happens to the energy supply chains. Just a brief note how we approach the angle of leveraging Earth observation, or how we call it increasingly Earth intelligence. It really sits in the middle. We are a data fusion company that combines maritime offshore data with onshore geospatial data and combines it with national statistics in order to create new insights and deliver them through a software as a service to clients. With that approach, we have created a European crude oil storage index, which in cooperation with Aresis, a spin-off from the Politecnico in Milan, which is a composite indicator that is combining a bunch of different things: Sentinel-1, Sentinel-2, AIS as well, maritime movements of cargoes, crude oil tankers in particular, and also the University of Oxford's COVID tracker to understand whether there were severe lockdowns or mild lockdowns happening in different countries or regions. How do we do it? How do we generate the index? We use the Sentinel-2 to detect and find, locate storage tanks in Europe. We do it globally, but in particular for this index in Europe. And then to leverage the Sentinel-1 data and interferometric techniques to understand the movements of the floating roofs. These will allow us to understand also what the changes are at dedicated ports in Europe. What did we do is we created index measures. Europe is surrounded by a key of logistical ports and locations that have superior importance because they are at choke points, at key points. I would flag Rotterdam being one of the most important ones, where a lot of commodities arrive and then get redistributed within Europe. So monitoring that will tell you a lot of what's going on. I think the origins of this index are going back to the commodity trading sector that has been using for ages the metric of inventories, because they tell you in one number the health or the status of the market and whether it is important or not. I would like to stress that while this index was created for COVID purposes, actually here and right now, it's also telling you how we go out of it, how the economy is improving. And I think we definitely advocate to keep the index on, because it will allow you to monitor things even way beyond COVID times. Just a technical aspect here. You can see the human eye is relatively good in the sense that you can see the floating roof tanks. These are crude oil tanks. Some of them are full, some of them are empty, some of them are half full. But if you have to do this at scale and every week, then I think it requires a more automated approach. So Sentinel-2 helps us to locate them. But then ultimately, show you here an example, we also look at the cylinder, the diameter, but also the displacement of the roofs, how they move up and down. And I think that's one way to monitor these locations, the inventories. Now, how do the Sentinel see the tank? You see here the example of Rotterdam. Rotterdam on the right-hand side here is the Sentinel-2 image. You can see it's a bit blurry, but it's very important for us because you can see we can monitor which tanks are in operational and which are not. Most of them are painted white to avoid the heat. Some of them are rusty, unfortunately, but a vast majority is white, and that allows us to locate them. And then we use the Sentinel to monitor the high displacement. It's important that you get a quick map from me to understand how important certain locations are in Europe on the ports. So you can see here, that's the oil infrastructure, courtesy of the International Energy Agency in Paris, that shows you that there's a full web of pipelines and storage and refineries across Europe that helps us that we can still have access to energy, oil in particular, and that the resupply works efficiently. This has grown for over 50, 60 years, and it's now in getting stress tested right now at the moment. What we do is we overlay that with monitoring a bunch of different sites across all of Europe. And those are not, they are chosen carefully. They are at neurologic point of the system, and they need to be monitored carefully to understand the health of the market. So going back on the indicator, you can go to the race dashboard. You will find a crude oil storage index here. And I chose here as an example Rotterdam because it beautifully shows how when you overlay also the Oxford data on the lockdown restrictions, you can see that we went into the market and the stocks kept on building. Why is that? All of a sudden during COVID, demand was falling away, but the oil kept on coming. And then all of a sudden you have stocks building up at the ports because the demand is not there. Most recently, however, we see a flip side of that, that actually the demand has been recovering. We go out of lockdowns and all of a sudden you have a relatively fast reconnection, and we are back now to pre-COVID levels in the port of Rotterdam. And actually you could argue not as bad as it is on the gas market, but energy supply storage gets a bit constrained, oil as well alongside gas. A second one is the German port of Wilhelmshaven in the north, which resupplies a lot of Western German refineries, the BP and Shell refineries. And you can see similar patterns that we had during COVID restrictions. Demand was falling away, stocks were building. But right now we observe an indicator that you can all access on the race dashboard that we go back to levels that we have seen before. And now the question that I have is really, and what we are following every day now, is what's happening now? Are we going even lower than that? And how what's here in what should we expect for the winter months to come? Do we have enough energy in inventories in order to get us through the winter? That's all from Storage Index. Thank you very much for your time. Happy to take any questions online, offline. And with that, I'm happy to pass back to Anka.
Thank you so much, Florian. This was very, very interesting and very, very timely with the with the gas crisis that is ongoing. So I will pass the ball now to Isabella Kausch from Vista. She will talk to us about the latest agriculture indicator that was added to the dashboard.
Okay, thank you for introducing. Okay, so I hope you see my presentation. And we are working within the project COVID Harvest and showing our results on the RACE platform and on two platforms even more. COVID Harvest, I'm working at Vista as a software developer, and Vista is funded in 1995 in Munich, and at the moment we are 22 employees. And from research and development activities, we developed many operational services. They are divided in two main segments, the hydrology and the agriculture. And we have services like yield forecasts or precision farming. And within the hydrology, we monitor snow and make runoff forecasts and so on. And within COVID Harvest, we analyze the impacts of COVID-19 on agriculture by deriving harvest dates and patterns using Sentinel-1 data. And it built on the extensive big data analysis framework of Ypsilon and added SAR analysis to it. Ypsilon I will explain then in the next slides later. But first of all, what was the study area? Of course, Europe, it was in 19 countries. And we selected about 200,000 points of interest. We looked at the vegetation period of last year, and we analyzed the crop types, winter cereals, winter rapeseed, and summer crops. And we derived harvest dates with an accuracy of 3 to 6 days, depending on the number of available orbits from Sentinel-1. If we look at some backscatter images from Sentinel-1, then we have the VH and the VV acquisition and the ratio VH-VV. And these three parameters are visualized as RGB composites here. And in the ideal case, the VV, the green band, will increase after harvest, but the red and the blue will decrease. So we want to see the harvest, but as you can see in the images here, it's not that easy to just find that out from backscatter. So what we do is we look at the coherence, and the workflow is visualized here. So if we have maize plants on the field, for example, and we have 2 acquisition dates, date 1 and date 2, then the coherence is low. After date 2, we have a harvest event, but the coherence stays low at all between date 2 and date 3. But only with date 4, if the after harvest, there is a high coherence, because these stable ground conditions after harvest will increase the coherence significantly. And this is visualized here in a time series of the coherence in the top graph. And at the vegetation time from July to October, the coherence stays very low, but after a harvest event or maybe tillage methods, the coherence increases significantly. But this is not enough. We use also the sigma naught ratio VH/VV to detect a harvest event. And if we look at the time series, the sigma naught will decrease after harvest took place. So we combine these 2 parameters. Then we run the algorithm for all our 200 POEs in Europe, and get as result for the winter cereals this map. And it's pretty nice to see that we have a very a great south-north gradient. So in the south, winter cereals are harvested much earlier than in the north, and this makes sense and is as expected due to the climatic conditions. So since the harvest dates have been calculated, they have to be examined in more detail due to COVID-19. And that's when Ypsilon comes in. So for this, we relate the calculated harvest dates from our algorithm with our Ypsilon service chain. Ypsilon is a yield prediction service chain, and it calculates the harvest progress according to natural factors by the use of the physically based crop growth modeling. Thus, the model predicts a harvest date that takes into account many measured variables and current information, such as satellite data, mainly Sentinel-2 data, weather data, information about the maturity stage of the plant, and soil conditions and topography. So in Ypsilon, we derive the expected harvest progress curve, here visualized in black, which describes the perfect time of harvest of the plant in a significant region. And what we can say now is that if the harvest date derived from radar is earlier than predicted with Ypsilon, then the plant was harvested green, and that's typical for silage corn or silage wheat. But on the other hand, if the harvest date derived from radar is later than predicted with Ypsilon, then this could be a temporal delay caused by COVID-19. And this comparison was done for all 19 European countries and all 3 crop type groups. And the result is, as we see here, exemplarily for winter cereals again, that mainly all countries are congruent with Ypsilon, but Hungary, Spain, and the UK show some delayed harvest. It's the percentage of delayed harvest at end season. But in the end, after we did an extensive research on COVID-19 cases and the restrictions in these countries, we can't reveal a clear COVID-19 impact. And in the end, of course, we published all our data on the RACE platform. That's why I'm talking here. But we also published our data on the food security tab, where a user can also download the data with the special harvest dates for all POIs. And we also have a commercial platform within our Ypsilon project, and there we also published our results. And maybe I can switch there quickly. Can you see the website? Is that correct?
Yes.
Okay. So here's always a small description, and it's an interactive website where we can click on a country. You can, on the right panel, select which crop type you want to see or investigate, and you have also the selection between the country level. So this is a bit smaller, and then you have also the regional level, where you can see all the single regions where we had our points of interest. Yes. Okay. Thank you very much for listening. Also, if you have questions, let me know. And yeah, thanks a lot.
Thank you very much, Isabella. So we reviewed some of the economic indicators, some agriculture ones, and now we move to the environmental indicators. So I would like to call my colleague, Christian Retcher.
Hello?
Yes, we can see your screen. Welcome, Chris.
Yes, I'm trying to share. For some reason, the audio is very low on my end.
We can hear you very well. So,
okay, very good. It's back. Okay, all right. Happy to speak on this occasion. My name is Christian Retcher. I'm working in Esrin. I'm the atmosphere scientist, and I will cover a couple of slides on the air quality activity related to the RACE dashboard and the challenges. So let's just dive into the matter. What are we talking about? Air quality parameters. Primarily, we've taken air quality parameters supplied by Copernicus Sentinel-5P mission, and that is nitrogen dioxide, NO2, and also carbon monoxide, CO. So what is that? How it's being produced? I mean, there was lots of that in the media, of course, probably more on the NO2 than on CO. Nitrogen dioxide is typically being produced by combustion of fossil fuels, but also in general a combustion process. So that relates, of course, to traffic, to industry, energy production, of course. So when you would just burn coal, for instance, to create electricity, but also heating. NO2 has a rather short lifetime of about 4 hours, and it's been diluted, let's say, in the atmosphere by either transport, so it's been blown away by the wind, or chemistry, so it's been transferred to something else like ground level ozone. Why do we actually care about NO2? NO2 is harmful to our lungs. So when you inhale a high dose of NO2, that is not good for you. You're not immediately dying from it, but in the long run, let's say 20 years or so, there's clear statistical data, medical data that proves that inhaling large dose of NO2 over that many years is harmful. What limits the capabilities of measuring NO2 from space? I mean, remember the satellite flies at an altitude of about 800 kilometers, and the amount of NO2 that we're trying to observe is in the under 1% range. It's actually much, much smaller than that, but just to keep this, keep that in mind. So it's a very, very tiny chemical species that we're trying to observe. Whenever there's a cloud coming in the way, we cannot see NO2. There's also meteorological effects that basically transports it away, or let's say it washes out of the atmosphere. So there's lots of dynamics also going on with this NO2. I already mentioned that. So the satellite flies over once per day and gets a daily total column. So basically the whole amount of NO2 that's been seen from the satellite down to the surface is being recorded. And that's quite a big change, a big difference to when people talk about surface concentration. So that's the surface concentration is actually the one that you inhale. This is the critical part. The sensitive spectral range for NO2 is between 400, let's say in the 400 nanometer range. So it's visible. So on a very polluted day, you actually see like a brownish layer of NO2 in the atmosphere. So you can actually see that. What we have produced for RACE, and I will then later visualize that, is to account for all these things I just mentioned, is 14-day running averages. And that's basically to smear out all these effects, you know, of cloud cover, wind, precipitation, all of that. The second product that I'll be showing later is carbon monoxide. Carbon monoxide is, of course, known to be quite a deadly chemical species if you inhale a large dose of it. But what we're seeing from the satellite, of course, is again the total column. So carbon monoxide is important to understand tropospheric chemistry. It's also been produced by burning fossil fuels, but also biomass burning. So it's quite a sign for biomass burning whenever you see CO popping up. But it also contributes to oxidation of methane, or is involved in the oxidation of methane in other hydrocarbons. Different to NO2, CO has a much longer lifetime, about weeks and months. So we're doing 3-day averages because CO is rather stable from one day to the other. The spectral band that we're looking at is 2 to 3 micrometers, so that's so-called shortwave infrared. You cannot see CO compared to NO2. Let's just quickly talk you through some of these visualizations here. So this is an image you have probably seen all over the place in news, in media, on TV, and so on. These are the typical changes in NO2 from 2019 to 2020, highlighting a couple of cities with, let's say, because of the lockdown measures, people were driving less cars, industry has produced less NO2 and so on. So the numbers are quite dramatic, but there is quite a large error on that. So for Madrid, Paris, Po Valley, Rome, we are in the 50% range of reduction if you take an average over months. But again, it's 15% of uncertainty. And that again relates to what I said before: precipitation, cloud cover, wind, chemistry. So there's many things that actually dilute the signal or giving precise numbers. But what you can see, the change of NO2 emission is visible. When it comes to the RACE dashboard, how did we visualize all of that? So because all these NO2 images are being processed offline, then pulled over to the RACE dashboard. You see in the large plot on this slide, you see the NO2 on the top right, and you see this little slider, so you can select 2 daytime ranges where the NO2 is being mapped, and you can slide left and right, and you see how the change is actually happening now. If you click on one of these cities in the center, and much of that has been talked by the speakers before me, if you click on one of these buttons in the center, then pops out a so-called time series. So basically for all these cities that you see there, we've produced a time series from 2018, so whenever S5P data was available up to now, basically following, let's say, daily and then averaged over these daily 14-month 14-day, I'm sorry, running averages of NO2 pollution. These pink bars, they show the lockdown. So whenever there's a lockdown, you see quite a dip in this NO2. Coming to one of these challenges that we were running, there was one recent one that's been closed already. And how does the pandemic affect shipping traffic and related air and water quality? And the objective there was to develop in integrated ways to characterize shipping vessel dynamics. Of course, we know ships also produce a lot of NO2. If there's less ship traffic, then of course you see that as a signal. Relevant to that is also if the harbor is sitting next to a large city, you have to basically disentangle the signals coming from the city, from the car traffic, from the industry on land versus what is happening on the harbors. And there was this one idea of the winner, Alessandro Cimbelli, who developed a Sentinel-1 based indicator count on anchored vessels and correlated that with Sentinel-5P data. Coming to the next slide, basically illustrating some of that. So NO2 levels, boat traffic. I mean, you can all go to the web page and basically click you through. You also see some kind of it's not really a time series, a histogram now over a couple of months, where you see how the total traffic versus the so-called scaled NO2 is actually behaving. Next is carbon monoxide. So remember what I said, carbon monoxide is a rather, let's say, slowly changing chemical species. When you look on the left on the plot, the high levels of CO, the reddish and orange color, are in the biomass burning areas. So there's Africa, there's also India popping up, some signals over China. What you can't properly see in this plot is like the world map, which is on the bottom right. It just didn't fit the screen here, so you see apparently a lot of CO production over Asia. Where is all these data coming from? It's been processed by a service called Sentinel-5P PAL, the mapping service. When you go to PAL now, you see the link on the bottom right. You can see NO2, CO. This data is available for over a year now, and recently there was some SO2 added. So sulfur dioxide is yet another pollutant that we are trying to monitor. That is not on RACE yet, but this is on the mapping service. And a final slide, quite a busy one, I'm sorry, is related to this RACE activity. We were running a study in parallel that was called ECOVAC. And the reason for ECOVAC is to also look into other species that are not so prominent, like NO2 or also CO. So I just mentioned SO2 reductions, for instance, over northern China, 75%, so quite dramatic. Formaldehyde reductions, 40%, glyoxal reductions, 50% around February time. Similar numbers are true for India, but one real reason to run that study is also to prove if or not there was a change in so-called XCO2. So XCO2 is CO2, of course, is the one climate gas, no, that many people are focusing on. And the question is the reduction of combustion, is that changing the CO2 signal? Because CO2 is co-emitted, of course, in every burning process, if you want. Whenever you create NO2, there's very likely CO2 being produced. But the answer is very simple. The signal is very, very weak because CO2 has such a high background that the additional contribution of CO2 or the reduction of CO2 is minimal. So you basically don't see these changes very easily. And there was this one case over China where if you look close, you can see a couple of changes, but not pretty much. So that's turning into a climate, let's say, into let's say, a forward-looking message means shutting down the economy for a number of months doesn't do much to save the planet regarding global warming. More needs to be done. And my final remarks on this study is, so it was a one-year study, created 19 peer-reviewed papers on all these things above, a number of presentations, press releases, TV coverage, ARD in Germany, BBC, interviews with Greta Thunberg, a MOOC contribution, so massive online open course. So if you want to go, you can click yourself through and you get all the interviews with the scientists. And I believe with that, I come to an end. Thanks for listening.
Thank you so much, Chris. This was very informative. We're staying with in the domain of air quality, and we have with us Stein Vermooten from ICMWF CAMS. Welcome, Stein. Thanks for being here today. Can you hear us? We cannot hear you for some reason, or I cannot. No, still not.
Stein, we see you, but it looks you are muted somehow.
Can you see me now and hear me now?
Yes, perfect.
Okay,
Yes,
so what I was asking, Anka, is if you can share my slides. So
I can share your slides. Yes, one
okay.
sec. Let me just load them.
All right. My apologies for joining late. We had a C3S Gala event, which overran a little bit. So I just joined to listen to Chris' nice presentation, and I think what we provide in CAMS is a very nice compliment. So
okay, so I should.
So just to introduce myself, my name is Stein Vermooten. I'm the head of section for user outreach and engagement at ICMWF, which also includes Copernicus, of course, and then the future destination Earth will also be part of my activities, at least to the extent of user engagement. Next slide, please. So I'm going to talk about the Copernicus atmosphere monitoring service. And I think what's nice to see here is how it complements what the satellite observations, and of course we have Sentinel-5P if we focus on Copernicus, what CAMS can provide as an added value. In a way, we see CAMS as user of what ESA provides on this. But what CAMS provides is a blending of observations, so satellite and non-satellite observations with models to provide a consistent picture. And this is based on the laws of physics and chemistry and advanced mathematical models called data assimilation. And by this, we can in fact make seamless maps. So because we can in fact produce concentrations for those areas where observations were not possible. But we can also look into the future. We can do forecasts some days ahead. And we also provide reanalysis of the past years and decades. What we also provide is our concentrations at surface level. And of course, when we talk about atmospheric composition and we look at it in scope of health, public health, it's at nose level, which that's the most important. So these are some elements which I wanted to highlight in scope of my presentation. Next slide, please. If you now focus on COVID-19, and there was a lot of discussion, of course, in the press, and in a way, COVID-19 was a certain blessing for those atmosphere monitoring specialists to assess what the impact is of a lockdown on emissions and concentrations in the atmosphere, and to see and improve the added value of Sentinel-5P, but also CAMS. And here's is a very nice example of a private company together with a National Meteorological Service from the Netherlands, KNMI, where they use CAMS forecast as a background because of the fact that we are generally quite accurate, and use it as a business as usual for their emissions. And by this, they could, in fact, investigate what's the impact of the lockdown compared to a normal situation. So it's a very nice example. Another example is presented on my next slide, where we supported the European Environmental Agency in their annual air quality report to bring together a lot of Sentinel satellite and machine learning methods and multimodal scenario runs to do a consistent evaluation of many different cities on how in this case, in the picture, NO2 levels have been reduced or changed over time, and where sometimes there's a clear signal which is not per se linked to the lockdown, but to weather and other factors which also need to be taken into account. So there was a clear need to make sure that CAMS was introduced into the race dashboard. Next slide, please. And that's why back in autumn last year, Anka called me and said, let's do something together. Let's collaborate, and let's see how CAMS can be integrated in the dashboard. And what we decided is to integrate service concentrations from CAMS for a couple of key air pollutants. So it's NO2, PM2.5, and 10 at ozone. And this at global level, and for selection of 50 European cities. And in fact, we only had a little time to do this, but it was very effective, not only because of the professional support at ESA, but also because CAMS offers the data and via a standard interface. So from our side, to make sure that all these things were integrated in the race dashboard didn't take too much effort. And this proved the added value to work with standard interfaces to make these type of things possible. So you see on the map where you can find the CAMS air quality data just below air quality data as Chris presented. And then maybe we go to the next slide. And one of the elements which we provide are time series. That's always interesting to see for 5 large cities in Europe. So all the capitals plus a selection of others. And these time series are providing information on how background air pollution has evolved since the beginning of the COVID-19 outbreak. So we started in February 2020. The values represent areas of 10 by 10 kilometers. So it's more representing the urban background. So it's not the local air quality levels which we measure, but background data. And then we combine this with information on restrictions on lockdown measures in place in the country where the city is located from the University of Oxford. And then you see like the bars which indicate high restriction, low restrictions. You see the values which are the mean daily values, the 7-day mean values, and then also we provide in gray, in fact, the background information from the past, from 2017 to 2019, so you can make a comparison. What's nice, and I can't illustrate it here, is that you can zoom into the map and you can drag out it, so it's really dynamic and it's very nicely made to provide value information, and of course you can also download it. The next slide, please. On top of this, we provide the map, the information in a map, and you also have here the slider and the ability to compare concentrations with the past. And in our case, it's starting as of October 2020 with information again on all these daily average pollutants. I think this is my last slide. Of course, if you have more information on CAMS, and if you want to use it for a certain challenge or to develop some additional indicators, you're more than welcome to contact me or to contact other colleagues. And yes, so this is my presentation.
Thank you very much, Stein. This was really, really nice. Very good to see all these products being showcased on RACE. We're staying in the area of environmental indicators. So we will now have a presentation from our colleague, Maria-Len, about water quality.
Good morning, everyone. So I will share my screen. Can you see my presentation?
Yes.
Can you see? Okay. You see it in presentation mode on the right way?
Yes, it's the right way. Yeah.
Okay, thank you very much. So thank you, Anka. I will now present the work that has been done to monitor water quality during the RACE experiment. And first, I would like to acknowledge my contributors for this work, so the team from the GNR who did work on the calculation and the production and the analysis of the indicators. So, as most of you know, so during the lockdown, there has been a lot of nice images on the social media and the newspapers showing incredibly clean waters all over the world in coastal areas. And actually, these restrictions that were put in place during the COVID represented a unique experiment of reduction of anthropic forcing on the environment, as we have seen now with the atmosphere, my atmosphere colleagues, and including, in fact, also the water in the marine coastal system. In particular, the places where there is usually significant pollution inputs coming directly from the urban and the industrial agglomeration through rivers. So it was natural to ask, and a lot of people actually were asking themselves if this water quality was improving because of the COVID restrictions and the decrease in pollution. And of course, we also wanted to check if this reduction could be detected from space. And actually, this was feasible because we have historically, we are using historically optical measurements on board satellite data to calculate, to estimate proxies of water quality. And in particular, we usually use chlorophyll A and tensile suspending matter that can be derived from, so in particular, and what I will be showing in this slide, from the OLCI sensor on board Sentinel-3 and the MSI sensor on board Sentinel-2. So the chlorophyll A concentration is an indicator of algae abundance. So to be quick on this, that fluctuates both naturally, so there is really a strong natural variability of chlorophyll A concentration in coastal waters due to the combined effect of winds, marine currents, upwelling dynamics, and so on. But also in coastal area, this concentration can be strongly influenced by river inputs and human activities, as a high concentration can result from discharge in the coastal areas of urban sewage, fertilizer, nutrients from agricultural activities. So this is routinely used as a proxy for water quality. And another proxy which is commonly used is total suspended matter, which is a concentration of organic and inorganic materials suspended in the water. And again, this is a proxy as different of water quality, as different contaminants, as nutrients, pesticides, metals can aggregate to this suspended material, and if in excess in the environment, they can alter the state of aquatic ecosystems. So this is naturally the two main parameters that we have been working on to monitor and to check the impact of the COVID on water quality. And so these indicators, I will explain in the later slides how we calculated them. But here you can see on the RACE dashboard, what has been done is to develop both maps, regional maps, and time series of two specific indicators based on chlorophyll and total suspended matter in three different areas of interest in the Mediterranean Sea that you can see here. So in the North Adriatic Sea, offshore the Venice Laguna, in the area at the mouth of the Rhone River in France, and offshore Barcelona at the mouth of the Ebro River in Spain. We also provide more regional maps of those parameters, but that comes from the Copernicus Marine Service, and this will be presented in the next talk by Vittorio Brown. So for each of these two indicators, we provide regional maps and time series, and also a story in the sense that we have performed some analysis and try to understand the variability that we have seen during the lockdown and in the last 2 years. So how are these indicators calculated? So we are using the OLCI again from Sentinel-3 full resolution data, and apply some algorithm, regional algorithm for the Mediterranean Sea to retrieve phytoplankton, chlorophyll, and total suspended matter, using different treatments for the different water cases, open or coastal. And then the OLCI daily time series is turned into a weekly time series by averaging on a pixel by pixel basis, and also averaging over 3 pixels per 3 pixels, so that at the end we have a 1 kilometer resolution weekly maps. And we calculated the climatology from this, using this weekly data from 2016 to 2019 to have an understanding of the climatological value of these parameters, which were then used as a reference for the analysis. So then water quality indicators were calculated as an anomaly, weekly anomalies of these two parameters with respect to this long-term climatology covering the 4 years from 2016 and 2019. So here you can see a map of anomaly in the Northern Adriatic Sea area. So when it's blue, it's a very low chlorophyll concentration anomaly, so as a proxy for the good water quality, and the orange is a high anomaly of chlorophyll concentration. And for specific points in the area, then we display on the dashboard a time series of those anomalies with a color code, where so this is displayed for the entire year of 2020, and you have the lockdown time periods indicated in pink on the time series. And so the color represent for each week, if we have a normal value of chlorophyll concentration in blue, low values in green, or high value in red. So this helps monitor the water quality for a long time period and for the specific area of interest. So what was quite interesting to observe during the Italian lockdown. So here are some maps in March April, and this was the case until the end of the lockdown in May, is that we could see on the North Adriatic, so the western part of the North Adriatic, and here you have the city of Venice and the Laguna of Venice, a very negative anomaly of chlorophylla concentration, so the proxy for a particularly good water quality over this time period. And you can see here the time series for the specific point, again with concentration of green dots. So obviously the question here was, okay, is that what is the story that we can tell? Is that due to the lockdown, or is there some other processes that enter into play? As I have said before, chlorophyll concentration can also vary due to natural processes. So the team did an exhaustive analysis, going in depth and taking into account many different other environmental parameters to check this hypothesis. And so I would do it very quickly, but it was a very interesting investigation. And what came out is that actually in the Venice Laguna, the pattern of low chlorophyll concentration during the lockdown period was most probably linked to the decrease of maritime traffic. This was highlighted using high-resolution Sentinel-2 images that were available during this period. So this is an example, for instance, of turbidity value, and it's where you have the blue value, you have a low turbid water, so higher water quality. And on the right, two last right plots on this slide, you can see that the channel that links the Venice airport at the north of the plot to the Venice city at the south of the plot was particularly clean during the lockdown with respect to pre-COVID condition. So this in the Venice Laguna in particular could be highlighted thanks to the Sentinel-2 images. But when you go offshore, the analysis that was performed could show that things are getting more complex, and that the natural variability and the main explainer, or the main factor for explaining this anomaly in chlorophyll concentration. So the team in particular could investigate it and find out that this striking negative trend in chlorophyll concentration was likely due to a very particular interplay during this period between different phenomena. And actually there was a particularly low winds and an increase in sea surface temperature. So the waters offshore the North Adriatic Sea was particularly stratified during this period. So with an absence of upwelling of nutrients, which means that this led to an anomaly of chlorophyll concentration due to this low nutrient inputs, which was also strengthened by the fact that, and you can see it on the left, during this period, there was a particularly low water discharge from the Po River, which is in the area, and a particularly low turbidity value of the Po River, which was linked also to this low water discharge. So all this analysis has been described and is highlighted in a paper which is in submission now. In this paper, a very interesting approach, also very interesting study, was to say, okay, so at the first order, it is clear that this anomaly that we can see in these water quality parameters are due to environmental factor. But applying even more in-depth analysis with sophisticated analysis tool, they could highlight or put in evidence the possibility that there is a second order effect that could be due indeed to this specific situation of the year 2020 and the COVID lockdown. And so using a multi-year hierarchical cluster analysis, so whether the reflectance of the optical sensor on Sentinel-2 is classified and the similarity between the spectra analyzed, they could show that there is a specific cluster of a spectral shape that could be recognized during the summer, during 2020 in conjunction with the lockdown. And this is also explained in this paper. So to conclude, of course, I invite you to read this paper to have more information on it. I have been very quick on that. But as a conclusion, just to say that in the frame of the RACE project, so we have been developing water quality indicators based on well-known proxies of water quality as chlorophyll A concentration and total suspended matter from Sentinel-3 and Sentinel-2. These indicator maps and time series are operationally displayed on the dashboard on a weekly basis for 3 areas of interest in the Mediterranean Sea. The team has been working on understanding the main factor behind the observed reduction in chlorophyll A concentration that could be observed from those data during the lockdown. And it was shown that during that the dynamic coastal environment, in those dynamic coastal environment, this satellite product were capturing mainly the first order variability due to oceanographic conditions and winds. And under particular environmental condition, we could also capture a second order signal. But of course, to further disentangle between the anthropogenic and the natural variability, further analysis are needed using ancillary data, in situ information on anthropogenic pressure and stressors. So there are still some work going on to add other areas of interest in the dashboard of the coastal European coasts, and also to work on other indicators, in particular on the sea surface temperature anomaly indicators, and again continuing the analysis to better understand the changes in the satellite product that we observed, and disentangling between ocean environmental causes and anthropogenic causes, and also investigating, exploring the potential of other methodologies as artificial intelligence to integrate different variables as sea surface temperature, winds, river discharge, as we have seen that they all have a strong impact on water quality in order to predict a better water quality over coastal areas. And with that, I will thank you very much for your attention.
Thank you so much, Marie-Hélène. We're running a bit over time, so I invite immediately Vittorio Brando, our next presenter, to the stage. And while Vittorio is loading his slides, I'd just like to stress that I think it was obvious from Marie-Hélène's presentation that it's very important to really understand the data that you're working with. So if we have participants in the challenges with us here today, that's an invitation to send us your questions and just get in touch with us if you have troubles understanding the data. So Vittorio, the floor is yours.
Thank you. So good morning, everyone. Thanks for the opportunity to present some information on the Copernicus Marine Service and its inputs to the RACE dashboard. So as a background, I wanted to explain for whom of you that you're not aware, what does the Ocean Core Thematic Assembly Center within CMEMS. What we do is that we bridge the gap between space agencies and the public by providing high quality product for the global ocean and European regional seas based on multiple ocean color missions. The main aim is to provide as many essential ocean color variables as possible. Those are obviously possible to produce from ocean color radiometry. And so in particular, we produce chlorophyll, inherent optical properties, phytoplankton functional groups, and the structure. The important point to make is that the regional products provide higher accuracy than standard global product, as there is a regionalization of protein chains that takes into account the bioptical characteristics of each of the regional seas. This is an overview of all the products that are currently in the Siemens catalog that are based on ocean color. An important point to make is that we have 3 series of data streams. One based on the merging of several sensors, or multi-sensor products, and 1 kilometer resolutions for the regional seas. Then the Sentinel-3 OLCI A plus B products at 300 meters for regional seas, and also the Sentinel-2 MSI products A and B at 300 meters. What we produce a level 3 daily product, a level 4 daily gap field and monthly average on a real time and a real process time series. And this one gives an overview of all the products that are existing as of today or in the catalog. As an example, for the 1 kilometer and the 300 meter production, the point I want to make here is that the regional products are produced using regional algorithms to improve their quality, and hence each of the different seas has its own processing chain that makes use of the local in-situ data for product definition and calibration and validation. And hence that's the reason why they receive different scientific publications done on the basis of the selection of the most adequate algorithm. That's another recent addition to the catalog is the Sentinel-2 based 100 meter resolution products, where remote sensing reflectance, turbidity, suspended particulate matter, and chlorophyll concentration are produced. Differently from the 300 meter 1 kilometer products, the chlorophyll algorithm here is produced with only one algorithm for all European waters. This is an example of for a given day of the level 4 daily get field. So you see that these are the strips of the Sentinel-2 passages for a given day. And this is the 100 meter with a 20 kilometer coastal stripe. And when you have a lot of island, like in this case, or in this case, the strip of available data becomes larger. So moving to the input of Siemens data in the REST dashboard, this is what is being shown already earlier by Marie-Hélène. So the Mary's, the OLCI 300 meter products are used for the production of the weekly climatology, of the comparison of with the weekly climatology, and so yes, for the assessment of the anomalies, and this is done for the Venice site with its own the relative total suspended matter and chlorophyll water quality regional maps and anomalies. The same applies for the Barcelona time series, and this one is the example of the time series and the chlorophyll concentration, and also the third site, so the Rome and the Marseille water quality time series. The other important point to make is that also we have the multi-sensor 1 kilometer data, which is we use in here the level the daily gap field data, which is then uploaded to the RACE dashboard and to provide a background of all the coverage for the daily fields. We could also add further than the multi-sensor 1 kilometer data, also the daily level 4 for the Sentinel-2 in the next future, because that would, and also that will show the higher resolution data. Thanks for your attention.
Thank you very much, Vittorio, for this great presentation. I now welcome the next speaker, So Patrick, I think you take over from here.
Thanks, Anka. Yes, good morning, everyone. I'm Patrick Griffiths. You see my slides?
Yes, perfectly.
Okay, great. So thank you, Anka. Good morning, everyone. I'm going to present a little bit of information on the race challenges in the context of the race initiative. So the race challenges that we have been organizing for the last 1.5 years are basically our effort to invite the community to participate in the investigations that we're doing using Earth observation and other geospatial data sources to investigate the impact of the pandemic on the environment and socioeconomic systems. So the idea is basically, you know, in the community that there might be some good thinking, and we want to invite the community to develop these ideas and contribute to the race dashboard. And the first round of challenges was held in 2020. Back then, this was linked to the Sentinel Hub eval script interface. And this first phase of challenges was basically, you know, submissions were evaluated on a weekly basis. And we had weekly winners with no real predefined theme, so it was very open. And we then initiated a second round of challenges in 2021 using the EuroDataCube Jupyter Lab environment as the interactive development environment. And we had several defined themes for the initial challenges that were on a monthly basis in March and April. And the latest call for challenges and for participation is open for 3 months and has four themes, defined themes. So here's a little a summary of what we did in the 2020 custom script challenges, where we had these weekly submissions, and there were a couple of good ideas there. And, you know, so there were some on water quality of rivers, some on vessel dynamics, some on construction monitoring using synthetic aperture radar, and then, of course, our famous examples of the truck detection and also the flying airplane monitoring. For the next new round of challenges, we switched basically to the EuroDataCube environment, where you have Jupyter notebooks available, and you can access all of the data sets relevant to the race dashboard, and also the existing indicators and other data sets. And with the team from EuroDataCube, we created some nice tutorial notebooks, where we also provide the links on a later slide, also with help from our engineering support teams. And these are really helpful resources for you to understand how you can use the many tools that EuroDataCube offers to access data sets, to visualize certain indicators, how to retrieve, you know, COVID statistics, to bring them into your multidisciplinary analysis and investigation. So the common goal for all the challenges is basically to identify innovative and new and relevant ideas and support these investigations, basically for geographic and temporal upscaling. And then basically the good ideas should really transition into new race dashboard indicators. And we have some presentations on some of these indicators today. So on the left-hand side, the example that Henrik Fisser is going to present on the truck detection. On the right-hand side, the team from Mauricio Pamplona, who's going to present this a little bit after this talk on the flying airplane detection. And then finally in the middle, this is the ongoing investigation from Alessandro Cimbelli, who's trying to characterize the vessel dynamics in front of major ports over time. So we'll have presentations in all of these three. And yes, so to transition these initial ideas into race dashboard indicators, we have set up this kind of roadmap where for the current challenge, participants basically have 3 months to develop their initial ideas using Jupyter notebooks and EuroDataCube, the licenses that we provide for that. And we basically offer here monetary prizes for the best ideas, €5,000 for the overall best contribution, 3,000 euros for the second best, and 1,000 euro for additionally selected ideas during the first 3-month phase. And then these selected ideas are basically invited to contribute or basically to work on EU level upscaling of their ideas, where we provide also engineering support and enhanced license packages for the EuroDataCube environment. And here we offer up to 10,000 euros for the best contribution that then needs to be upscaled to a relevant European level spatial extent and relevant temporal extent. And then finally, we would then invite those upscaled contributions again to transform their upscaled analysis into a formal race dashboard indicator. And there we offer another 5,000 euros for each incorporated indicator. So altogether, you know, this is quite an attractive reward, summing up to 20,000 euros if you do well. And for the current challenge, we have 3 themes that are defined. That's transport and pollution, socioeconomic impacts, economic recovery of the pandemic, and also an open theme. So if you have additional ideas that you want to work on, that's fine too. And this current challenge period is open from 1st of September until the 30th of November. And we have the links here and also on the later pages. So the themes that we have defined, just 2 examples here, the transport and pollution, which is quite openly defined, and it's basically looking at the relationship between changing transport patterns in shipping vessels, or also with trucks or road transport, and pollution, environmental pollution that you observe using Earth observation data sources, such as Sentinel-5P for the atmospheric parameters, or also the nice CMAMS datasets that were highlighted from in the previous presentation. So the idea is, you know, how can we demonstrate this link between changing transport patterns and the resulting pollution patterns? And we presented some ideas on how this could be approached, but it's really quite open to the participants to lay this out as they want. And the second theme is looking at socioeconomic impacts, which is traditionally a hard theme to approach with Earth observation data, but there are some good ideas on this, and we provide some example questions here, how you can approach this, and you know, using different small proxies to then define a more complex indicator is one idea how you could do this. But basically here we want to see, you know, to what extent varying phases of the pandemic affected socioeconomic patterns across Europe. For all of the challenges, the evaluation basically follows these set of criteria. So what's the innovation potential? Is there cross-disciplinary value? Because that's, of course, what we're kind of targeting here, because the race dashboard brings together all of these interdisciplinary data sets and some easily implementable analytic methods. What's the scientific integrity, and is validation considered? What's the upscaling potential of this idea? Some ideas cannot be upscaled. And is there a joint use of Earth observation and other data sets? And also, is there a relevance for European policies? Okay, we offer a whole range of technical support elements here. The most important is the technical guide that Anke and colleagues have developed here, which is really rich and valuable information for any participant, showing you, for example, how to access existing indicators, data sets, how to create custom dashboards, where to find the tutorial notebooks, and the link for accessing that is here. The challenge rules and resources I explained here, and there are also our support email addresses here. And just an additional point here, we're happy to organize a Q&A. If there's an interest, just drop us an email. Okay, and with that, I would invite the next speaker to follow up here. We have now 4 additional presentations that will look at different aspects of the race challenges. We'll start with Stefan Meisel from EOX. We'll describe a little bit the EOX workspace for the challenges, and then we'll have Henrik Fisser, Mauricio Pamplona, and Alessandro Cimbelli demonstrating these community contributed indicators that they have been developing. I'll hand over to you, Stefan.
Thank you, Patrick. Can you see my screen?
Yes, looks good.
Excellent. Okay, so yeah, thank you for all the introduction. I want to use my 10 minutes to give you a overview of the resources that we provide for you as a participant. And I not only want to do this with the boring slide sets, but I try to do a real life demonstration. Let's see how that goes. So for the registration step to register to participate at the contest, go to this link. Don't worry, it will be shared afterwards as well. So I recorded this registration step, which I obviously did before the session, but you use that link, you just register for an account. So you provide your usual things, an email address that's important so to stay in contact with you. You can also use other authentication methods, so like the COI, for example. And here you register, now you have an account at your data cube, and then you just, okay, we want the country, your country for statistical purposes, but that's really the only information. So, yep, you accept, of course, the terms as usual, and then you click the participate link. And with this, we get the information that you want to participate, and we will provision the workspace for you, including all the services that we provide. And I will show them in a second. So it's important. It's no need for you to do anything from now on. You will receive an email once this is done. We will provision that for you. Okay, but with this, now let's go to the live demonstration. So now, as I said, you will get notifications that your services are subscribed. So once you enter your data cube dashboard, that's how it will look like for you as a participant. So you will see, just a second. Excuse me, that's the joy of working home. Okay, so you will see here the services that you get, the Sentinel Hub subscription, GeoDB subscription, and of course the workspace, the EOX Hub promotion workspace. Sorry. Okay. So in this workspace, the most important thing, of course, is the Jupyter Lab, as Patrick already said earlier. So I have this open here already. Okay, I had it opened too early. So again, that's how it looks like. So it's starting. And what we provide you in this Jupyter Lab environment is that you, once it's here, right? So you have down here, you have the EOX Hub ties, your data cube ties, and we get the README for the race challenges. So again, it's a textured description of the challenges in general. But what Patrick already mentioned, most importantly, is the Jupyter notebooks that we provide here. So tutorials on the various services that are available and how to access the data, the indicator data that are provided for the challenges or in general for the dashboard. So let's start with the first one. You select it. So in this case, it's just rendered. You can read through it if you want to, but of course, you can always execute it interactively. So you need to copy it in your workspace. And once you have it in your workspace, you can really run through the notebook and execute it interactively. Excellent. Okay, so here you see the list of indicators that we have available. And for the demonstration, I've chosen the same indicator that Marie-Hélène presented. So it's the water quality time series. We call it N3. So well, you can connect to the GeoDB in this case. So I'm showing the GeoDB access for the vector data, obviously. So you see we have this indicator at the 3 locations here. And then you can, of course, always retrieve the data and plot it. And now I hope that this fun is recovered. Yes, temporary hiccups. Sorry for that. So I run through it in order to be able to plot it now. So we are downloading now the data from GeoDB, and we plot it for one city. And in this case, I believe we selected Barcelona, right? But what you can do as well, I mean, you see here the data now, and you can use the data for whatever integration you want to come up with. But what we can also do is, of course, we can add interactivity already in the notebook here. So in this case, we simply make the city selectable. So we can, for example, go to Venice, the Venice Lagoon, and see the indicator there. Yep, so this is what I wanted to show for the GeoDB. But let's go to other notebooks, and I have them already opened here. So for example, we have the second notebook that I wanted to show is the process API, where you can get access to all the raster data and also the data sets that are used in the various indicators. Just note that they are on different infrastructures, so you have to use the right collection ID. Okay, so we have here prepared a population density data that is used in various indicators. So we just retrieve the population density of one country, which is Austria in this case. But you have always, of course, the full, as Gregor explained in his presentation, the full list of data sets like the Sentinel-2 and others. So here we make a simple request for Sentinel level 1C and level 2A data. And we can also have Sentinel-3 data. And various output formats. So there's a lot of flexibility in the process API that I invite you to explore. I'm not sure how I'm doing in time. Maybe I show quickly because I really like it, but then I leave the rest to you to explore the statistics API that also Gregor already mentioned. And here, as you can see, we connect to the data that is on different instances of Sentinel Hub. And so also data that was using the bring your own data functionality for the dashboard. So in this case, we are connecting to Sentinel-1, Sentinel-2, and 3 again, and we are retrieving the data over this area of interest that was shown, and now we are plotting it. And in this case, it's aggregated over time. So you see on the x-axis the time, and you see this different data over time aggregated. But, and this is now maybe more interesting, we have lots of data that is specific for the indicators like temperature or humidity and wind. And again, we just show a quick example how to retrieve the data, and show it over time. Again, the various layers. But of course, you not only get the aggregation and the mean, but you get standard deviation and other statistical parameters, as you can see in this graph. Okay, let me stop with maybe just one quick mentioning of the X-Cube. So you can also have the X-Cube and X-Cube Gen service and connect to those to have real data cubes and an X-array in Python. Well, and the last thing I wanted to quickly show, once you are done with your new indicator and you have a submission that you want to do, so you please place everything in one folder, like I did here with some sample files. You can use Python notebook files or just Markdown files to have a textual description of your indicator. And once you're done, just right-click on the folder, and then you find here a menu entry which says Submit Directory for Race Challenge 3. And when you click this, then you confirm, and that's your submission. You can always redo the submission, so we will get this in the point of time. We will copy the whole directory, and you can always, of course, redo until the end of the challenge. well, that would be my quick introduction to the resources that you can use as a participant. And I invite you to participate in the challenge, and I'm looking forward to see a lot of submissions. Thank you.
Great, thanks a lot, Stefan. I think we have to move on. We're a little bit late in time here. I think we have to move to the next presenter, which who is, I believe, Henrik Visser. But certainly a very nice result submission interface that you have created there, and a lot of great resources. Really invite everyone to take a look there. Henrik, please, the floor is yours.
Yeah, thank you, Patrick. Very happy to be here today at the side event about the race dashboard at ESA Phi-week. I'm going to present about the track detection indicator based on Sentinel-2 that I contributed to the race dashboard last year. So my name is Henrik Visser. I have graduated from the University of Würzburg this year, and this work has been done in the framework of my master's program. We're looking at the indicator about the number of tracks in the race dashboard, which you see here. And trucks in general are really, it could be called the heartbeat of the economy, because, for instance, in the European Union, 75% of the inland freight is actually transported on roads. Now, this is also why countries use that as an economic indicator in near real time. So this is a truck toll mileage index from Germany, and here on the left, in April 2020, May 2020, we see that drop that is clearly associated to the first lockdown during the COVID-19 crisis. Initially, 2 years ago, potentially, if someone had asked me if we could detect trucks and create some kind of indicator similar to a mileage index, maybe not as close, but just in general, I would have said, yeah, maybe you can do that with very high resolution data. But I've shown last year with my idea, which contributed to the contest, that we are actually able to see and also to detect moving trucks in Sentinel-2 data, which is because of a sensor effect, the multispectral instrument. That's the sensor of the Sentinel-2 satellite. It has an interband parallax effect causing a temporal sensing offset between these bands. And here on the left, we see that this is up to half a second, for instance, between band 2 and band 3, and another half a second between band 3 and band 5. And that's how we are getting these kind of reflectance signatures that we see here on the right. So these fanned rainbows on roads. Essentially, what we see there is a truck moving. Okay, it could also be an object of similar size, for instance, a bus, but that at the stage of developing this, this has been the assumption, and it has been validated since then as well. Now, the initial method contributed to the race dashboard relies really on only a small part, or a third of the truck in the RGB spectrum, and that's the blue part, exploiting this outstanding or this remarkable reflectance there, as the blue reflectance is superior compared to the green and the red reflectance. And the very simple method uses two ratios between the blue and the red and the blue and the green, and then targets these trucks, assigns a point, and then filters surrounding points in the direct neighborhood in order to be sure that only one single point location is associated with the truck detection. We have some detection examples across Europe presented here on the right. For the race dashboard, there has been an initial validation using traffic count station data in Germany, and we depicted here in red the number of cars counted by the station, in dark green the number of trucks counted by the station, and in light green the number of trucks counted by the Sentinel-2 method on one acquisition on the 8th of May 2018. And we see that the magnitude of trucks here is correct compared to the cars. So this already confirms that we're actually not detecting cars, but trucks. That's a clear sign for that. I would say that after some more validation approaches, also during my master's thesis, that the figures here below are the rather correct depiction. So it's usually an underestimation of a third or even half compared to the station data, but that varies on the top. In the top figures, you see that it can be better as well. For the race dashboard, I have created an indicator comparing a baseline, which comprises the years 2017, 18, 19, and then always the period between the 1st of April and the 21st of June, and then comparing that to the COVID year 2020. Only Tuesdays, Wednesdays, and Thursdays were considered to exclude those days with lower truck traffic, which are the weekend days and the surrounding days, Monday and Friday. So I would like to give you, walk you briefly through the indicators. Here you see the race dashboard, which you might already know, and we click on the number of trucks. And here we have the opportunity to look at motorways and primary roads. See here the detections in that period depicted in 10 by 10 kilometer cells. So 4 periods, 3 baseline periods, and then 2020, you have some information here on the right. And we can zoom in and actually explore that in a very customized way, selecting an area of interest here, looking at the Rotterdam port and the surrounding and motorways. We recognize that the baseline years all had more trucks detected than the 2020 year, and also draw a customized, even more customized AOI multi-polygon, and have a look what's there near the port of Calais, the connection basically between Belgium, the port of Calais, and there as well, we actually recognize that there has been a decline. It's not as clear as here in all areas. If you explore, you will see that in some areas there was even a rise of trucks detected in the period in 2020, and other areas it's just stagnating. So it's really diverse across Europe, and of course we must also keep in mind that there might have been some catch-up effects already. Here, for instance, 2019 is higher, but the other years there's no clear pattern, neither an increase nor a decrease. We then zoom in, we can also actually explore the real detections. So here for 2020, we see the point locations of the detection trucks detected in the Sentinel-2 data in that period. Yeah, and we can compare that as well with other periods, 2017, 18, 19. For primary roads as well, we can just do a similar process and have a look at our customized AOIs. Here, for instance, that's Paris, looking at the primary road indicator for Paris. Actually, really quickly, the graph is appearing, and we see that, well, here again, we see a decline of trucks. But there are other areas where it looks completely different. Let's compare that to the beautiful city of Rome. How does that look? And here, appearing soon. Yeah, it's not as clear. You might see some differences, but worth to explore more. And of course, you can just visit the race dashboard, and along with many other fascinating indicators. You're much welcome to explore this, and also to ask questions and share your results of your own explorations, maybe in your own country or area of interest. So overall, as said, the picture is quite diverse. Here it's depicted, aggregated on the whole country, whether there has been an increase, a normal situation, or decrease of counted trucks on motorways, and recognize that actually 58% of the countries show decrease, while 29% of the countries even an increase, even more than 20% in Spain and Germany, for instance, stayed nearly still, stable, And that might also be related to some catch-up effects that were already captured in the 2020 period. I want to hint to a last thing. So detecting tracks with Sentinel-2 data, it has been something new. Others have exploited that effect already for airplanes, for cloud detection, but also for ship detection, for calculating also velocities. And I've been pursuing that method or that promising idea in my master's thesis, and also developed the next version, let's say, of the track detection method, and then being actually a real object detection method, delineating the whole track object, and also calculating the heading, the speed, and that has been extensively validated on a global basis using labeled data, and then on a local basis across the country of Germany using 26 traffic count stations. Here we see that there's quite a good fit between that station and the Sentinel-2 counts. Thank you very much, and I would like to thank everyone who has shown interest and supported this.
Thanks a lot, Henrik. Fascinating results, and great that this is still ongoing as a scientific investigation. Also, for anyone to know maybe that Henrik's idea, which started as a little prototype script in Sentinel Hub, that it has now transitioned to an on-demand algorithm that can be consumed by anyone in EuroDataCube. And we're planning to reprocess entire European coverages of the track detection for the last years and for 2021 as well. So that's really a great evolution of the product. So we'll move on to the next presenter, which is Mauricio Pamplona. Welcome for joining us, and thanks for joining us so early. I assume you're still in the US. So Mauricio will present his community contribution to the RACE dashboard. Thank you.
Okay. Can you hear me and see my screen?
Yes, perfect.
Okay, cool. So my name is Mauricio, and I'm going to present our indicator, which is the indicator about flying airplanes. This was a collaboration in between 4 universities, USF here in the US, and then UT, FPR, and Unicamp from Brazil, and NTNU from Norway. And well, the base of our indicator is similar to the previous indicator that you just saw. So we originally intended to detect parked airplanes, and by looking into airport images on the EO browser, we noticed that we could actually see the moving airplanes as this RGB pattern. And then we actually moved our idea to detecting flying airplanes, because this would give us a better idea on the impact of the COVID-19 into the traffic of airplanes. Because even though we had some impact in the number of flights, sometimes the number of parked airplanes did not show a big change. And yeah, basically the same effect that you saw for trucks is what happens in airplanes, but we have actually a second cause. So airplanes actually are high above the ground. They are not necessarily on the ground, only when they are taking they are parting from the airport or arriving. So we have these two causes in here. The first one is actually movement from the satellite. Since we have a small time lapse in between the color bands during the acquisition, the satellite actually sees the airplane from different locations in each of the bands, but we also have one object that is traveling at high speed. So if we consider that the 3 bands were captured with certain delay, but that satellite wasn't moving, we would still have some displacement in the object in the ground caused by the speed of the airplane, and that's why we can actually see the aircraft in the runways, because they are not high in the air. So this effect in here doesn't play. The first one doesn't play a role, but the second one does, and we still have the 3 colors in the airplanes. And in these images in here, you can see actually the 2 effects together. So in some cases, the airplane, they leave some tracks in there, and we can see here the direction of the airplane because of the track. And we can also see the direction of the satellite because of the displacement in between the tracks in each of the color bands. So we can see that the satellite is going from up down, and we can see the airplane in here in the first example is going from the left to the right. And then we created a whole framework that would process satellite images and would end up with some analysis of the traffic of airplanes around some airports. The first step to do that was to select some airports in Europe to do this analysis. We got the list of the 30 busiest airplanes to do this analysis, and we got a nice coverage around Europe by doing that. And we split this this group of airports in two groups, training and testing, because we wanted to check if our method was going to generalize to unseen regions. Then we used OpenStreetMaps to define the location of each of these airports that we selected. And then we used the Sentinel Hub to download a large image around the airport. Because we cannot look for flying airplanes only in the airport region, you can see here that the airport region is only a very small piece in the area that we are looking for airplanes. This area has about 6,000 square kilometers for each of the airports that we are processing. And this area is going to give us about 20 minutes of coverage. This means that we can see airplanes that are arriving in the airport in up to 20 minutes, and aircraft that departed the airport in up to 20 minutes ago. So it's only a small window, but we can see a decent number of airplanes by doing that, and we can have a decent idea about the traffic of this specific airport by getting this kind of area. And then the way we detect these airplanes is by using neural networks. So we are using one type of neural network that is called fully convolutional network. And basically this network is going to get every small patch in this image, and the size of this patch is 51 by 51 pixels. And it's going to classify it as either an airplane or background or soil. In this case, like it's not going to be an airplane. And this sizing here, we basically computed it in a way that we would cover the speed of any commercial flight. So it can get airplanes traveling at up to 1,800 kilometers per hour, and this is twice as much as the average commercial flight speed. And well, the main problem with us was actually annotating the images so we could train our network. So the way we actually managed to do it was by doing a semi-automatic approach. So we first got only a small number of images and annotated a few airplanes there. We trained one classifier by doing that, and then we did rounds of detection on the training images, followed by manual inspection of the detection to discard the false detections. And then we would retrain the method and then do it again until we got a detector that would work well for the training airports. And then we would check the performance on the test airports. In here, you can see some challenges. We can have clouds that are going to affect the detection of the airplanes. We can have some displacement between the color bands that is going to create like the same RGB pattern, but for buildings, or we can have noise on ocean areas. And all of them are going to affect the result of the detection. And this is not something that we can train to be robust to, because usually they are like random patterns or they are too similar to the airplane. So if we train to ignore these regions, we are not going to be able to detect the airplanes. So the way we actually solved that was by doing some post-processing. So we basically ignore all the areas that have too many clouds. We also ignore areas that have like missing data. And finally, we check how many airplanes we detect in each of these small blocks in our entire image. And if we have too many detections in one of these blocks, we are going to delete this block as well. This is because after actually annotating some images using our semi-automatic approach, we actually saw how many airplanes we usually have in each of those blocks. And we saw that we never have more than 5 airplanes in a single block. So if any region has more than 5 airplanes, we would discard it. And then we do a masked average of the detections over time for all the images that we can get for an airport in 1 month. And we can create like monthly estimates of the number of airplanes around this airport. And you can see that we end up with a curve that reflects the impact of the COVID. So for each airport, we do have a reference number of how many airplanes we expect to detect in one image. And we can see that during the COVID, if we have high restrictions, we can see that the number of flights is much smaller. And when we have like some, we don't have so many restrictions, the number of flights start getting back to normal, which is these blue bars in here. We also did some quantitative analysis. We saw that we have less than one false alarm per month per airport, which is quite good with our artificial intelligence approach. In here, I'm showing some of the detections. You can see that it's very robust to many variations in the aircraft. We have like big aircrafts, medium aircrafts, very small aircrafts that we can barely see. So the images in here are magnified. We can detect airplanes in the ground, and we can have occlusions because of missing data or clouds, and the method still works. In here, we have some of the cases of false detections, and you can see that in most cases, they are caused by noise or clouds. But in some cases, we do have like some colored patterns in the ground that also cause misdetections, including trucks in the road sometimes. And in here, we compared our results to flight track records from Open Sky Network. This is a website that has like the tracks from real flights. And you can see here, the yellow circles are our detections, and we are detecting airplanes in the same locations where we have records on Open Sky, which are the pink circles. And you can see that we have a lot of flights before COVID, and during COVID, we had a reduction in the number of flights, and our indicator is going to reflect that. We did some manual measurements to check if it was working, and at airport level, we do have some noise in our measurements. But if you combine several airports, you can see here that our estimator, our indicator is very stable. This curve is showing that we actually reconstructed the signal that was created with the real number of flights from 42 countries in Europe. We got this data from Eurocontrol, and we can reproduce the same behavior. We can actually measure the impact of COVID very well using the images from satellite data. And basically, as a result, we got one award from the race competition, and we also integrated our solution to the race dashboard. They did a publication about our idea, and we released all the code and all the data in case you want to reuse that for other indicators or any other application that you wish. And yeah, that's my presentation for today.
Thanks a lot, Mauricio. Great results. Let's move on to the final speaker because we're running heavily over time here, which is Alessandro Cimbelli. Mauricio, thanks a lot, and it's very interesting. And also, I really like the way that you normalized for the varying number of observations from Sentinel-2. That was really well done. So really good contribution here. Alessandro, are you ready to present?
Yes, yes, thanks, Patrick.
Fantastic.
Well, I don't know if you can see my presentation here.
Not yet.
Not yet. Okay. Okay. Okay.
We see you. That's the first step.
Okay. Well, now, can you see here?
Yeah, it's coming. Yeah.
Okay. So, well, good afternoon, everybody. Thanks, Patrick. Well, I'm going to present you a study about a possible indicator of the vessel number extracted from the Sentinel-1 images that are in the anchorage areas of the main European hubs, and could be seen perhaps as a complement of the the analysis that has been done by Florian of OilX about the crude oil storage indicator. During the COVID-19 pandemic in spring 2020, one of the main effects has been the dramatic fall of oil, crude oil prices, as we can see here in this chart. And in particular, the fourth block, all the transportation, has had a dramatic impact even of the on the airline jet fuel. The direct consequence of that has been that the onshore tanks have remained full, and the oil tankers has remained blocked and anchored off the main hubs, waiting for unload their load. The study has been has focused on this area in the English Channel that are in front of the main European hub, Rotterdam, Antwerp, and Amsterdam, in particular during all the year 2020. And Sentinel-1 images have been used to detect, to count these vessels that are in these areas. At the same time, I have compared the number extracted from this kind of processing with the carbon monoxide values collected by Sentinel-5P over the same area of interest in order to understand possible correlations. So the approach has been to extract the outer borders of each vessel from the images and convert them as an array. This has allowed to classify ships according to their size also. The results of a correlation has shown that in the first stage, has shown that there is a correlation of 0.66 between a moving average of 10 days of the number of vessels during the whole year with the value of carbon monoxide of the Sentinel-5P. So it's a good starting point, in my opinion, to understand. This is a short animation that shows the number of vessels, and we can see that during the days of April and May, it has increased a lot the number of small points in this area. Currently, I'm in the upscale phase of this study, so the main objective are now to extend this analysis to the around 30 main European anchorage areas and commercial harbors, and to extract, to derive some other parameters from the Sentinel-1 images, like the area and perimeter, as well as the width, length of the vessels, but at the same time to integrate with other services that come from the Marine Copernicus that can give information about the sea currents and the wind in the position of each vessel. So that could be interesting to understand if even the position of the vessels, of each vessel. And at the same time, as a main objective, I want to classify ships as immersion or anchored. So that's it, my short presentation. So I hope it's all clear.
Fantastic. Thanks a lot, Alessandro. This is an interesting investigation, and we're really looking forward to supporting you further in the upscaling process.
Okay.
So thanks a lot.
Thank
I
you.
think we had originally foreseen a little question and answer session here, but I think given that we're 20 minutes over schedule, I think we will simply remind you that there are support email addresses and that we can organize a question and answer session ad hoc if needed. So Anke pasted the support email address here again into the chat. And I thank all the presenters from the challenges, and I hand over to Anke for some final words.
Yes, just to thank you so much, Patrick. So just to echo Patrick's words, we are really looking forward to receiving your questions, and we have this email address that is always ready for you. You can also, I invite you to visit the GitHub, of course, and to provide us feedback there. You can also open new issues and request new features for this project. So yeah, keep in touch.
Thank you, everyone. Bye-bye.
Bye.
Thank you very much.